So, giant ionic structures. Unlike with covalent, where we may have simple or giant structures, ionic is nice and straightforward. We only have giant structures. Before you watch this, do make sure that you are completely happy and completely on board with ionic bonding, because if you're not, this will be harder than it needs to be. So, let's just have a quick recap on ionic bonding. Ionic bonding, it occurs between metals and non-metals. Metals having a tendency to lose electrons, non-metals having a tendency to gain electrons. The phrase we use at GCSE is energetically favourable to. That means the metals are going to lose electrons to form positive, that's just a bit of shorthand there, positive ions known as cations, and the non-metals are going to form negative ions known as anions. Those oppositely charged ions will attract each other with an electrostatic force of attraction, and that then gives us our definition, as you will know from ionic bonding: the electrostatic force of attraction between the oppositely charged ions. As I've mentioned in other videos, depending on which order you watch this in, the whole basis of the properties of a structure is the interactions between the particles in that structure. And if we are dealing with a giant ionic structure, the particles within that structure and the particles that must be talked about as we write our explanations are the oppositely charged ions. Okay, so being a giant structure, giant being infinitely repeating a big crystal, we have lots and lots of oppositely charged ions, and the forces between them are strong. So, therefore, if we look at the melting points and boiling points, what are we doing? We need to be breaking strong electrostatic forces of attraction between oppositely charged ions, i.e. strong ionic bonds. Let's just write that in. And because these bonds are strong, let's just highlight that because it's important, because these bonds are strong and because there are many of them, they are going to take a lot of energy to overcome. Let's just write that in. This requires a lot of energy, and because it requires a lot of energy, the melting point and boiling point must therefore be high. And that is generally going to be the case for all giant ionic structures, i.e. any structure with ionic bonding. Let's just write that in as well. So that's in now. Let's recap. Melting points and boiling points. I've written boil points. It really should be boiling points, but never mind. In order to melt or boil the structure, many strong ionic bonds are broken. This requires a lot of energy, which means the melting and boiling points will be high. It all comes down to what you are breaking, what you are overcoming, and whether that is weak or strong. And in ionic structure, a giant ionic structure, what you're overcoming, what you're breaking are many strong ionic bonds. And because they are strong, as I've said before, they require a lot of energy, which means the melting points and boiling points will be high. Moving on, we need to look at conductivity. As you may already know, to be able to conduct electricity, we need particles within the structure which are both mobile and charged. We need particles, let's just put them in a little box over here. We need particles which are both mobile and charged. So we need particles which are both mobile and charged. Now, the key thing about this when I answer an exam question, you can't just say particles, you must identify what particles you're talking about. So conductivity. Well, if we take a solid ionic, are the particles mobile? No, they're not. And what particles are we talking about? We're talking about oppositely charged ions. In a solid, the ions are not mobile, therefore cannot carry current, therefore no conduction. Solid ionics do not conduct electricity. So let's just go no. Solid ionics do not conduct electricity. What about liquid or aqueous? We aren't going to talk about gases because gases are a bit strange when it comes to ionic gases, but liquid or aqueous, we can deal with that. So liquid, i.e. when we've melted it, or aqueous, when we've dissolved it up in water, is this going to conduct? Well, in a liquid or an aqueous ionic substance, ions are both mobile because they can move around, and charged because they are ions, therefore can conduct electricity. They can carry a current, they can conduct electricity. So solid ionics, no, they don't conduct. Liquid or aqueous, yes, they can. Why? Well, we've got the same particles in both. We have ions in both. The ions are always charged by definition, but in the solid, they are not mobile. So if they're not mobile, they can't conduct. In liquid or aqueous, they are charged, the ions that is, and they are both. And this is important, they are both mobile and charged, so can conduct. At this point, if you wish, you can pause the video and go away and make revision notes, get your head around these fundamental properties. Because what I'm going to do next is I'm going to do a quick run through on a sort of an exam style question, which is a comparative question, a melting point comparison between magnesium oxide and sodium fluoride. Now, the first thing you do whenever you're doing a comparison question on melting points or boiling points is you look to see what sort of structure we have. And here, both have ionic bonding and a giant ionic structure. In terms of exam technique, we must, or you must, because I'm not doing the exam, you must talk about both the bonding type, tick, and the structure type, tick. Just because the word ionic is in giant ionic structure doesn't mean you will get the credit for saying ionic bonding as well. Those are two separate things. They need to be written out separately. In this case, because both of the compounds we're dealing with have the same bonding and the same structure, we need to look within the structure to see why they will have a different melting point and boiling point. If I was comparing at this point something that was giant ionic, like say magnesium oxide, and something that was simple covalent, such as water, I would then just write out why any giant ionic structure had a high melting point, that would be the explanation above, and why any simple molecular or simple covalent compound had a low melting point, which is explained to you in your notes and in another video. Here, however, we are looking at two things that are both the same structure. They are both giant ionic structures. So, wherein lies the difference? Well, what we need to do is have a look at the oppositely charged ions that make them up. So if we look at MgO, MgO contains, well, what ions are in there? Mg plus 2 and O minus 2 ions. NaF contains Na plus 1 and F minus 1 ions. If we have bigger charges, we will have a stronger attraction between the particles. If we have lower charges, we will have a lower attraction between the particles. Therefore, we can just write, and I'll write it in for you in a sec, that if we have bigger charges, as we do on the magnesium and the oxide ions, we will have a stronger electrostatic attraction, which will require more energy to overcome, hence a higher melting point or boiling point. You obviously could argue it the other way around with lower and less. Okay, so that's written in for you now. Let's just run it through with a highlighter. Because the charges on the ions in MgO are higher, the ionic bonds between these ions are stronger. The electrostatic force attraction between these ions is stronger, requiring more energy to overcome. Now, a lot of people leave it at that point and lose a mark. We haven't actually answered the question. Therefore, the melting point of MgO is higher. So we need all of this to answer this question. It is probably worth 4 or maybe even 5 marks. So it is worth looking at and getting your head round. Quick run through again. When doing a melting point or a boiling point comparison, the first thing to see is what sort of structure you have in the two things you're comparing. If they are different structures, different bonding, different structures, state that, and then you can just do the normal why one is high and one is low answers, which are in the videos. If they are the same structure and you need to therefore compare them, you need to state that they have the same bonding. You need to state and what it is. You need to state they have the same structure and what it is, and then look within that structure to see why they might be different, as we have done with this. As with all of these, it is worth going away, making your own revision notes on this, breaking it down, practicing it before you move on.